This is based off of a review packet. You're going to see these from time to time. Sometimes I make them, sometimes I get them from your actual textbook. Please be aware that when I do something like this, not everything potentially will be on here per se. Like, you still have to understand what we've been studying, and I always have an actual review sheet, like gases 4, for you to study from. But it's based off of sections in the book. So if you're not sure, like there's one at the ending that does van der Waals equation. I told you what that is. That alters a real gas and an ideal gas. We aren't doing that. So it's not like you're responsible for everything on here. I've highlighted certain ones I want to do, but whatever ones we do, usually ones around that area. So let's say we do number 6, probably 3 through 9 are probably all very similar, and probably ones that would be for the test. On the back page always are all the answers. Look at that. So you can do extra practice. Now, I don't expect you, I've never expected anyone sitting here and doing all of them on here, but it does give you the benefit of potentially doing something extra if you're like, I need a little more practice. Then you have something that you can rely on besides all the worksheets and other things that we've been practicing. Okay, so just keep that in mind. As always, we record this. It's recording right now. So these are all the things that are on the test. I showed this the other day. I don't remember when, but you've had a nice preview into it. Tomorrow we'll talk about our test, or our lab, a little bit more. I was working with Morgan tonight, and their molar masses were like 0.2, which can't be. So I gotta figure out a couple things if some of our data, it's usually something that we're using that is off. So we'll get it together. Okay. So let's get into it. I have preset numbers. If you want to work on some of the things eventually, let me know. If you're seeing this at home, you need this packet. It's pretty confusing otherwise. So I would be doing this on scratch paper with me. If you want to try to squeeze it in, that's fine. But I am jumping right to number 10. So it says, a gas has a pressure of 3.2 atm and occupies a volume of 45 liters. What will be the pressure, or what will the pressure be if the volume is compressed to 27 liters at a constant temperature? I'm going to be very upfront. The test on Thursday, there will be a bunch of just gas laws. Just can you do all sorts of different gas laws? Yes, there are ideas and concepts and free response, but most of the front's just a bunch of little situations that'll take you like 2 minutes each, a minute and a half each. Like, can you do this stuff? So I'm going to give you a moment. Can you lay this out? I would really appreciate, like, I don't know, I'm hoping I don't use this one. I almost did. Let's just say it was this one. It's not. If it was this, I would really like that we're laying it out first. Like, you should actually write out the equations. Okay, so please write out the equation. It's not this one. I hope I didn't copy that down right or wrong. What equation do you think you're using? Okay, so we have this general relationship, right, of PV over T, right? So what am I using? What's my equation? Please plug in your numbers with all units, and then the one you're not finding should, let's just say it's V2, put it as V2. Like, that's how you show your work. I don't need to see all the little math and the division and the multiplication that's happening if you're plugging it in correctly. If you don't know what I'm still talking about, you will after this. So I'm going to pause this and give you about 30 seconds. So it's going to be PV over T. Right. You got me. It's going to be P1 V1. Quickly, our brains go to that. So we got to just make sure that they match up. Some match up really well, some don't. This one matches up really nicely because I'm not trying to trick you into where you don't know which one correlates with what. If they were both in milliliters, do I have to change them in the liters? Do I have to change them in the liters if they were both milliliters? No. If volumes were meters cubed, I don't care. As long as the units are the same in these laws, okay? In the before and afters, that's kind of what I call them, the ones and the twos. As long as they're the same, that's fine. What's the only thing that matters for units? What's the one that, Seth? They have to stay the same, but there's one unit that, Kelvin. Temperature has to be in Kelvin. It's the only rule. But you are right, Seth. You are right. And you broke another one. So, what do we get? Does the pressure go up or down? What's the answer? What's the pressure? What's the answer? You know what? If you're sitting there, you should be able to say that that went up beforehand. Why? The volume goes down, so it shrinks So pressure's got to go up because you've confined it into a smaller space. So pressure has to go up because there's more collisions. Collisions are going to more than double, or almost double. Okay, so that's number 10. Let's jump to 7. And there's a bunch of them here. I'm not going to do them all. I don't think we need to practice a lot of these, and we'll practice a little bit more tomorrow. So here's a question. A quantity of gas at 27 degrees Celsius is heated in a closed vessel until the pressure is doubled. To what temperature is the gas heated? What I want to see you do some sort of work to prove or show what the answer is, okay? So you can't just come up with an answer. How are you going to do this? Your mind should go into a framework of an equation. And we had an example of this like 4 times. No one asked me any of them in class, but I did answer a few of them out of the class. If you're given scenarios, you might need to come up with random numbers that make sense to this situation. Okay? So if you want to work with someone else, it's not overly complicated, but can you execute it? So I'm going to pause it here, see what you can come up with. So anybody want to help? Edgar, what equation did you use? Okay, yep, so Gay-Lussac's law has P and T relationships. Now maybe you can just visually see this, but I'll tell you now, a lot of people get this messed up when you start talking about degrees. And the reason why is this. This is an indirect relationship, problem number 10. Meaning when one goes up, the other one goes down. Okay? This one's the direct relationship. When one goes up, the other goes up. If I double one, I double the other. If I cut one in half, I cut the other one in half. Like they have the same effect. So if you say that the pressure is doubled, in theory the temperature should be doubled. But here's the trick. It does not go up to 54 degrees. Okay, that's the other reason that we have to use Kelvin. Kelvin, it's a big deal. It doesn't just go up 27 degrees. And oh my gosh, the pressure doubled, only 27 degrees. It's got to go up a lot more. So it's got to be in Kelvin. So you could come up with a number that would make a lot of sense if you're needing to show your work. So I have 27 degrees, so right away that's 300 Kelvin. You don't have to ever show work for Kelvin conversions. And then basically I'm asking for what the new temperature is. Well, in theory right there, it has to double. So you make up something. It doesn't matter what you want to do. You can say 1 ATM to 2 ATM. It doesn't matter. But if I'm asking you to show your work, or somehow, and there's other ways to do this, but this is one easier way to do it, is just show, I mean, you could do algebra and have x and then 2x and all that stuff, or you can just do it like this. And the answer, I hope that this would make sense. It's 600 Kelvin. But it's not 54 degrees. Oh, 27, doubled, 54. It doesn't translate that way. And that's why Kelvin is also really important to be used in these equations. That wouldn't be enough to double a pressure by just raising it by that much. So, right. Not totally switching gears, but let's apply something a little different. And we're 18. So we're getting into a different section. I'm not going to say anything. Besides reading, what is the volume of 16 grams of sulfur dioxide at 20 degrees and 740 torr? Show me the work and the answer. When I say work, I should see some sort of an equation. I should see numbers and units plugged in. Then that's it. You don't want to break it down any more than that and just show me an answer. That is fine. If there's an extra conversion that needs to be done that's not temperature or something with the metric system, then you do have to show that. Like i.e. moles, you got to show that. Moles don't just show up. You have to always show that. So that would have to be one T-chart. So what I'm hoping to see from you is a T-chart and a gas law of some sort. Go for it. Whenever you see grams, your instinct should be moles. Evelyn, do you have a molar mass for me on that? 64? I will trust you. So what is that, a fourth? Yeah. All right. So Chris, what'd you do then, in general? What are we applying here? Perfect. I even love how you did it. It's ideal gas law, but I love that you rearranged it. That's the ultimate way that I would love for you to do it. That's the way I learned it. I learned it from a teacher that really laid it out and did it well. And hopefully that makes sense to you. If you want to just plug it in a PV equals nRT each time, that is more than okay. But if you can plug it in that way, that's just that much better of a story, I think. So now we plug them in. Temp, where are we? If you cannot remember, this is the problem though, if you can't remember this, you still have to be able to get there. If I want to turn my torr into ATM, I would take 740 and divide it by 760, right? Problem is, if you remember 760, you could just take your R value and multiply it by 760. So either way, you could figure this out. The difference is, by converting a pressure, you actually have to sometimes show your work, or I can just have a new R value. And I'm going to write, what is this? 62.4. If you don't feel like that's important for you, that's fine. But I think it's invaluable as a speed thing and just a flow to my writing gas laws of just knowing the different R values. So I multiply, I divide. It's not a question of what the unit is because this is an ideal gas law. They have to be set. It's always liters. Ideal gas law has strict rules. If you're not sure what they are, they're on the R value, which is on your orange sheet. Like they're right there, like the units. Nathan, what'd you get for an answer? 3 sig pigs, I love it. Is that right? Love it. There you go. 6118. So that's how we do it. That would have to be shown, the moles. Whenever you're converting, if you feel like, oh, that would be a teacher art, and it's not a conversion of like a unit, like a simple unit, moles need to be shown. If this was an actual AP question, this would for surely be worth 2 points, and 1 point would be just for that, amazingly enough. It's amazing. And if you don't show it, you don't get it. So start getting into the habit now. Again, all front page. It's a gas law fun. So can you do it or not? Okay, so 20, number 20. Sorry, I wasn't sure. And you're done with that, we're gonna double this up. We're gonna do 20 and then 29. So I'm going to let you go at your own pace. Get 20 and 29, please. I'm going to pause it. If you want to work with someone else, check your answers when you're done with someone. So number 20, Nolan, what you just, in general, what are you applying to that one? What are you going to use?
PV over T.
Okay, so combine?
Yeah.
Good. So I hope, and if you're not doing this, just understand that my wording might be show the equation first. Like maybe you'll get a point for just the equation. And then a point for like all the setup and then a point for an answer. That's an easy way for me to grade it. Did you show me the equation? Or all the numbers with the units in the equation? And then do you have the right answer? 1, 2, 3. Done. That's an easy way for me to fly through a test. So that is correct. This can be easy and it can be hard. If they list both pressures and both volumes together, and if the wording's a little confusing, then you got to slow down because you got to be like, okay, which one's with which? If they don't, like 20 bails you out. I mean, my gosh, the volume at that temperature and pressure, that there isn't a lot of confusion there. So you got to just be mindful though that it could get a little messed up as you go. All units need to be written. I don't think there's much more to be said about this one. So the fact that I'm going to run a room. Convert it to Kelvin. And then what is the temperature? Sorry. Okay, question. I didn't read through this whole thing. I just saw the beginning. Is this actually needed to be ideal gas law? Grant, why not? Because pressure is the same, right? And you're not wrong. I thought it was going to be that too. I didn't actually read the second half. I just saw, oh, they have 2 more numbers and they're asking for a third one. I'm like, I want to do one combined tonight. Normally that's not the case. You wouldn't give them all. You wouldn't have to put them there. So this could totally just be V over T. But if you already set it up, it's not like you have to erase it. at all. Just make sure you're getting this right then. So in this case, you cross multiply and divide. So the volume went up, so the temperature should go. Think about a ball in the summer or the winter. The balls should get more inflated, it got more inflated, so that means the temperature went up because the molecules sped up. So the ball would, basically the molecules get heated up. So what's the temp? What do you get? Or else I can just look in the back. What do you get?
629.
If you're like, whoa, that's way too big. Think about what we did just a little while ago. If this doubles, this has to double. That's more than double. So that's an okay number. Believe me, like, you don't have a basketball and it increases, like if you're freaking out about the temperature, like even if it gets 28 degrees warmer, it's not like the basketball expands. Like, my gosh, it's taking up the whole garage. It takes a lot for things to expand. So temperatures will get a lot larger to get that big of a volume. But you get to 29, and then we're going to shift gears here. And we used what? I'm going to go kind of quickly on this. There's a reason why I did this one. That is the, what? What is 29? There's a huge hint. Megan, what'd you put? What are you using for 29?
22.4 liters per mole.
Ooh, interesting. So you did, oh, I would have done that. You did a T-chart?
Yeah.
Okay. That's one way to do it. That is definitely a way. You could have done this. So let me guess, you did this. Like that? Okay. What's another way? That is totally right. What else? Did someone do something different? Evelyn? So you did ideal gas law. Okay. When it has the word moles, you can the minute moles comes up and they're giving you other things, well, what other things did they give me? They asked for volume, and STP, Stone Temple Pilots, means temperature and pressure. So I have all those variables. So I totally could have done nRT over P again. What do I put? And this is what, I just want to show this one. So we've viewed what STP means. STP means standard temperature and pressure. What's the standard temperature? It's 0 degrees, so I'm writing 273. And what pressure? 1 atm. Now, that's also 760, right? Torr, 101.3 kPa. It's all those same ones, right? Either way, you get the same answer. Megan, I'm glad you did that. I did not think that direction. I bet each person kind of chose one path or the other. Either answer should get the same. Why can we use 22.4? Because that would be what 1 mole of it would be, and then that just plugs right in. So it's the same concept. So either one would be more than acceptable. So, okay, let's jump down. Very good. To 31. Little change of gears, but not completely yet. And today I'm more about reviewing some things we haven't done for a little while. We're going to hit a little more gas stoichiometry tomorrow in class, although we are going to try to get to one today. We have 4 more problems. Technically. I can pick a lot more, but I want to hit 4 more. These are going to start getting a little larger, though. Not too bad. So, an unknown gas has a density of 7.06 grams per liter at a pressure of 1.5 atm and 280 kelvin. Calculate the molar mass of the gas. I have no idea why, but students make a lot of mistakes in this one. I think when they get to the test, they space out on what they're doing, and I don't think there's any reason that we should be. I hope we went to that. I hope. If they ever give you mass and volume, how does that happen? What does that look like? If I gave you mass and volume, you had this in your lab, how does that change? Density is mass over volume, correct? So if that ever comes up, and I throw that out there, you don't have to solve for density and re-plug it in. I'm not asking what the gas is if you're looking for it. believe it's asking what it is, saying what is the molar mass. I'd have to give you more information. I think it's an octene or 9, octine, you don't know what that is yet. It's 8 carbons with, I think, 10 hydrogens, something like that. So either one would work. It just depends on what you're given. In this case, you're already given the density. I see everybody looking and trying to find it. Units, don't forget a unit. If you forget one, it's going to be half point right away, like right off the bat. So this one, there's not much to it. I will probably have a question that will refer, we'll have one tomorrow for an unknown identity, and you have to actually predict what it is. To get it right, you should get around 108. What, for the last half a point, if this is worth 3 points, what is my unit? Grams per mole. That is important. If you don't get it right, you will lose a point, or a half point probably. For molar mass, it's grams per mole. It's important. Make sure you get that. Every unit matters. Think of that as like the final little test. Like, we're not just doing gas. Oh, gas laws are easy. Great. Are you getting all the little parts of it too, though? You're getting all your units and everything else correct. Okay. Here we go. Let's you know what? We're gonna shift. Let's do that. Let's just do that. 34. This now is very different. You're gonna need a little space. So let's lay this one out. We're gonna do this one together. I'm gonna let you work a little. I'll do some stuff, get you going, come back and forth. It says a sample of 26.81 milliliters of a 0.1 molar HCl reacts completely with a rock containing 3.164 grams of calcium carbonate. What would be the maximum theoretical volume of CO2 collected at 30 degrees in 1 atm? Woo! In chemistry, what do we always need? Whenever I read a problem like this, and it sounds like there's a reaction, I need an equation. I can't do anything without an equation. What does an equation do for me? It organizes everything. Okay, so let's get there first. So I hope you have enough room. If you're way on the bottom of your paper, you might want to... So it looks like HCl reacts completely with CaCO3. When it says reacts completely, it means that it's going to completely make as much of the product as possible. So, anybody have any ideas of what is made? What is it? What are the products? I mean, this looks like a standard double replacement. Okay, it is. So every time we make a new compound, we got to think about charges. CaCl, close. CaCl2. Now, hold on. Do you see the I would not test this yet. Later in the year, you would know more about this. What does it give you? Doesn't it give you a hint of one of the products? What does it say? CO2. Now, think about, I just want you to realize this. Do we agree that H and CO3 are going to go together? Okay. I'm going to write this really small. You just might want to jot this down. That's carbonic acid. So, just think about this for a second. If this was a really, like, you're out there by yourself and you got to answer this question. It's telling you that CO2 is made. So what do you think then carbonic acid breaks down into? Close. If it's not H2, what's the other option? Look at how this breaks down. If I take CO2 out of here, what's left? What's left if I literally take CO2 out? H2O. Don't let that throw you off, please. That's why we're doing this together. Okay? You'd probably be given the equation for something like this for now. Later, you will have to know that. We learn more and more about how certain things break down, that extra step. Okay, balancing. I'm not sure if this is right. Like I'm doing this right now from scratch. I don't see anything else though already. Doesn't it seem like, isn't it funny when you write a bunch and you're like, there's got to at least be 2 of them. And then it's like, oh, okay, what do I do now? I want to organize. Put the stuff, put your information underneath it. So I have, where am I? I have 26.81 milliliters. I have a 0.1 molar solution of HCl. Reacts completely with this. saying that CO2, it says what is the volume at 30 degrees in 1 atm. Like this would be a big problem. I'm not acting like this is quick and easy. This is big. There's a lot of steps here. So realize that this would have like an A, a B, a C, a D to it. Okay, and you'd probably be guided a little bit. Okay, so instincts or feelings. What kind of, okay, if I'm given information about many different things, I hope that this isn't a secret. This is stoichiometry. Right? Like if I'm trying to solve for this and I'm given information about that, that's stoichiometry at its purest form right there. So, if I'm doing stoichiometry, what unit am I going to eventually need? If I have to go from one thing to another, I always need moles. Moles? Moles. I always need moles. So here's always my goal. I always want to get everything in the moles, or at least the ability to get onto my flow chart. Get onto my flow chart, right? I got to at least be able to get onto this, right? So if one of these units is already on that flow chart, great. I feel good about that one, right? That's there, okay? How can I get to here? If I'm going to the other side, can I go straight down on this line under these conditions? No, I'm going to have to take a detour, so eventually I'm going to need this. Just talking out loud here. So, I have two pieces of information. Doesn't that sound like a limiting reactant problem? So, what do I need to do with this? Moles. So, let's do it. All I got to do is this. You can do it however you want. You can set it up two different ways. If you're unsure, this is the easiest way to do it, I think. I like setting stuff up in the relationship. If you don't like that, here's the other way to do it. I'm just showing you two different ways. See how if I just multiply it? I like writing molarity, though, as moles over liters in a situation like this. I visually see that the liters are going to cancel, right? So I'm going to be left with moles. Both reds you don't have to do, just one of them. Whatever you like. I like the top one. I think that's more like molarity equals moles over liters. I plug it in that way. So you could figure out, though, I just want to show you this, you could figure out the limiting reactant without doing everything. Meaning, if I can just figure out moles of this one, is this 100? Anybody? Yeah. Is it approximately? Like 100.1? Is that better? Isn't it? Because it's like 40.08 plus 12 plus 16 times 3. 40.08, yeah. It's not working for me. Okay. So, I know that's just dividing by 100, but I'm doing a more precise number here. So, how can I do this? By looking at these two, just by looking at that, which is my limiting reactant? HCl or CaCO3? HCl, because I need to have twice the amount of this. For that, I don't even have more of that. I have less of it, right? So HCl is going to go completely down there. So now, I'm already there. I'm going to take this number. I'm going to do a mole ratio to CaCl2. So it's 2 moles of HCl to 1 mole of CaCl2. And why am I only going that far? Because I can't go any further. I'm already here. I can only go to here because I can't go down that path. I'm not at STP, right? So I'm going to divide that by 2, and I'm going to just make sure I have the exact number here. And now, I meant CO2. CO2, it's the same number. Sorry, CO2. It's all good. Mathematically, we're good. And now I plug it in. And this is how I would like the notation to go. I'm solving for volume of CO2. When you do this much and you start to do an ideal gas law in the beginning or the end, the first variable at least should have a subscript that's telling you what I am doing. I personally, I don't write it really big at this point because I've already written a lot. I like to write it like that, but if you're already into it, great. At least get this down and into it then. So are we in, what pressures are we in? Are we ATM? Oh, 1 ATM, okay. Temp, 30 degrees. And then I plug it in. And I hope that it comes out clean. Three or what was it? Okay. That is better. All right, so that is the math. That is how that works. Remember, we didn't have to do limiting reactant here because it was really obvious. And I was going to talk about the hint in the beginning of the problem, but I didn't want to because I wanted to show the math. If you read number 34 again, the first sentence, see how it says HCl reacts completely? What that means is that literally HCl is gone. That is a limiting reactant. But what happens when those words aren't there? We should be able to compare and see. Okay? Go to 44, please. Sorry about all the distractions here. Getting off my game now. Root mean square. I will give you what you are going to be given on the test. Okay? So that will be given either on your test or on the board or something. It's all that's going to be said. What is the root mean square of oxygen? And when you're done with that, because I just need to quickly do something here, go to number 45. Okay? Please. So, whatever you need to do with it, do it. That is how it should be done. You got to use the 8.314 R value. Obviously, your temperature's got to be in Kelvin because the R value has Kelvin in it. And then your mass has to be in kilograms. So this is of O2, so it would be 32 grams per mole. So you can convert your 32 in 0.032. Otherwise, just always take any mass you have and multiply by times 10 to the negative third. It's a lot cleaner. And then it's always meters per second. Okay? So there will be one like that. I don't want to trick you, but most people forget the kilograms or they mess that up some way or the other. Okay? 45. Great question. What is going on? We have two left and we're done. What is going on with kinetic energy? So what happens to the average kinetic energy of a mole of an ideal gas if? So basically what I'm wanting, and don't look on the back please, what I'm wanting is basically like, does it increase, decrease, or no change? That's basically what we're looking for, okay? Increase, decrease, or no change. So what I'd like you to do right now is commit. Commit to that idea if you have not already. Increase, decrease, or no change. So First one says the volume, and don't be confused if it says, whoa, of an ideal gas. All that means is that it acts perfectly. We don't have to worry about any other situations. It's going to behave exactly the way it should. If you increase something or decrease something, it's going to follow the things that we've kind of understood. So the volume is doubled, resulting in a decrease in pressure at constant temperature. The temperature is increased at a constant pressure. Absolute zero is obtained. And if an answer has to somewhat be tweaked, like, hey, increase, decrease, or remain the same, doesn't quite explain this as well as I'd like, then you can tweak that answer as well. So in general, what happens to the kinetic energy? So A, do you want to tell me what happens to the kinetic energy when the volume is doubled, resulting in a decrease in pressure at constant temperature? Anybody? Jordan, what would you say? If it's doubled, so the pressure decreases at constant temperature.
Is it the same?
Why is it the same? Constant temperature. Kinetic energy is based on temperature, right? So there'd be no change whatsoever. Okay? Kinetic energy remains constant when temperature remains constant. What is absolute zero? Absolute zero is temperature is the base the basis of motion and movement and energy that comes off of that. Absolute zero is when nothing moves at all. So there's zero kinetic energy. So letter C tricked me. I was really doing well on my explanation, and then I ended it. Darn you. So letter C. What happens to the kinetic energy when we reach absolute zero? It not only decreases, it's zero, because that is absolute zero. There's zero kinetic energy. I'm curious what the answer key says. It goes to zero. So it's zero. All right, it doesn't just decrease. There's nothing. That is the actual definition of absolute zero. There's no kinetic energy. There's no motion. There's no movement. And then what's the last one? When temperature is increased at a constant temperature or pressure, then my kinetic energy, it's not complicated at this point, should go up, right? Temperature increase, it increases. What gets you is that little sheet, we're going to do one again tomorrow, is when you start getting a bunch of different questions in a scenario, all of a sudden you get tricked. And you're like, oh shoot, I forgot, or I got messed up. That's when it gets you more, okay? Not when it's purely on just that. Last one. How are we doing on time? No, we're right where I want to be. 47. I know I didn't get into as much depth on some Stoic and some other things like that, but got to focus on one thing or the other. And I'll be honest, the bulk of the questions, I wanted to make sure tonight that we were kind of hitting things that we haven't seen in a little while. Calculate, this is a good one though. Calculate the rate of effusion of pH3 molecules through a small opening, so that's just effusion, if NH3 molecules pass through the same opening at a rate of 8.02 centimeters cubed per second, assuming the same temperature and equal partial pressures of the two gases. Okay, if you're like, whoa, what? First, you have to figure out how much faster one is over the other. So, this is just me thinking. I have pH3 and I have NH3, NH3. Which one's faster? Which one infuses faster? Shouldn't even be able to have to do a math. The NH3, because it's lighter. So I like to always do the faster one on top. And watch how I set this up. I hope this will make sense. I don't care about that rate that they gave me yet. I need to know how much faster one is than the other. So what I do is I do rate of, I always like to do the lighter one over the heavier one. We take the square root, and what do I do with those masses of these two? What happens? They flip, right? So the 17 will come down here. Technically it's grams per mole. I'll probably look the other way if you just write grams, but if you just write 17, that's a huge problem. We never write a number without anything. Gotta have something. But let's be technical here. 33.97. We got calculators. Right? I think I got that right. Yep. Please don't forget the square root. I cannot tell you the number of times, I don't know why, but people just get excited like, I divided! It's like, you didn't take the square root. There is no unit. So, this is the hidden part of this problem, but I think it's a good problem to have the discussion on. It says that the rate of this, of NH3, I've lost it. Now maybe I should have done the other one, is 8.02 centimeters cubed per second. So how can I figure out the rate of pH3? This is saying that NH3 is that's what it's saying. So how could I do this? Yeah. Would that work? I don't know. I'm just asking. It would. You can also, if you had the other number, you would multiply it because it would be as fast. So if you're uncertain about that, you can take 1 over 1.41, and then it's basically 71% of that. Yeah, 8.02 divided by 1.41. You have half. Not half. You have the fraction of that. That's one way to do it. Otherwise, if you had done the other way, you did 1 over 1.41, you get that the other one is that much times slower, and then you can take that. These are both right. And you can multiply it by, it's 70% of that answer. Either way, I hope you get this. And if I'm doing this, that's not actually right yet. What do I need? Centimeters cubed over seconds. Well, we don't do that. It's the unit that they had before. So it would be the same unit. Make sure that you clean that up at the end. Okay? So, and that is the answer basically in the back. If it's slightly off, it's because of rounding. There are a lot of problems on there if you want to practice, but you also have gases 4 to keep you occupied. I would probably wait on your gas law, your lab, until we kind of work things out. Although, start getting it into the equation. Like, you don't just sit back. Like, you got to know if your numbers are working. It won't help if you don't, but that's not due until Thursday. Thanks for coming. I hope it helped a little, or at least gave you some confidence, and we'll see where we're at.